Lefteris made my life easy because he introduced a lot of RPKI concepts. So my name is Amreesh. I work for the Internet. RPKI timing. So as you know, time is important as anything else in life. As Lefteris was mentioning, if ever you see that your BGP announcement is being hijacked, you will want perhaps to create an RPKI object and try to protect your routing, but you would want to know how much time it takes on the internet for it to have an impact eventually on traffic. And so this is what exactly we measured. So this work has been done in collaboration with a few other people, and you might recognize some names here. So the whole system, Lefteris also pointed out that how brittle BGP is. So when BGP was designed, it was a design with any security inbuilt, any validation mechanism inbuilt. So it was mostly based on trust. So it still is. Obviously, with time, we have improved the system a little bit. We have added, layers of security on top of BGP. So, for example, you have the Internet Routing Registry, where operators can go there and document their routing policies, and this information can be used to build filters. But we have seen that over the years, Internet Routing Registries got polluted with, outdated information. Some routing registries can allow anyone to come and add objects there. So not only it pollutes the database, but it can also contain a lot of wrong information which can be used for bad purposes. So we decided to come up with a new system which is based on a crypto system. And this is what we call RPKI, because it is based on a public key infrastructure. So when you have public key and private keys, you can use the private key to sign object, and this is the whole basis of the new system called RPKI. So it does provide verifiable sources of information, and it is at least in my opinion, the best way that we can go forward to secure BGP. So BGP has two components, as mentioned earlier. It has the origin part, where we need to protect origin of an announcement, but we also need to protect the path. So right now, what we can do is only origin validation. So we create objects through the RPKI system called route origin authorization objects, called ROA objects, in which there is an authorized AS, and which is allowed to announce that prefix, right? So it is up to the prefix holder, the owner of the prefix, to go and create those ROAs in their RIR's RPKI system. Then on the other side, when routers will receive those announcements, they will use that information in the ROAs to go check, the announcement I'm receiving, is it a legit one? Is the AS that is in the announcement allowed to advertise a prefix? If yes, I will let it in. If not, I will drop it. So this is what we call the route origin validation ROV process. There are 3 states in that process. Either it is valid, so there is that information in RPKI, or it is invalid, so there is a conflicting information, or it is not found because that information is not in RPKI at all. So to give you a little bit of a global picture of how this measurement study was done, we network engineers, we like talking about planes. We all know the control plane, which is about BGP, IS, OSPF, all those routing protocols are on that layer, exchanging routing information. And then you have the data plane where there is actual packet forwarding. But we also have the management plane where we can control some of the or configure some of the systems that we are going to work with. So think about SNMP, and RPKI is actually on the management plane. And for us, here in Africa, Afrinic is the one providing the RPKI service. So to have access to RPKI, you need to access the Afrinic portal, and from there, once you have your RPKI engine activated, then you can start creating the ROAS. So this is what we call the hosted mode of operation of RPKI. It is also possible, if you're really interested to host your own RPKI system, which means you will work in a delegated mode. That's possible. Not possible at the moment with Afrinic, because they are not offering the delegated service, but other RIOs are doing that. You can install a software, an RPKI CA software. One of the famous ones is Krill, and from there you can manage your own RPKI environment. But right now everything is done on the RIO portal, which is Afrinic. So in this study, we are going to look at everything RPKI related and BGP related. So we are going to look at what point we are going to time at what point a ROA was created on the management plane. We are going to look at the impact on the control plane, and also on the impact on the BGP, on the data plane. So this is just another illustration of the three planes. So this one is the control plane. So here you can see ASers on the internet sharing routing information using BGP to other networks. Some networks are doing ROV, like the one in green, or some networks are not doing ROV. So they would take the full BGP feed without filtering them. The others would do filtering. And so on and so forth. So this is how routing information propagates on the internet. And you also have route collectors. Lefteris mentioned about route collectors, which are extremely important for us researchers. So we use data from these collectors to see, at what point we are receiving those information that was that we announced. So our main concern here is time. How long does it take when you create a ROA up and until it touches BGP and the data plane, so basically your traffic. So first of all, the first and foremost timestamp is when someone creates a ROA. So you log into your RIO portal, you would create a ROA. So we have a timestamp called the user query timestamp. Next, so in our case, Afrinic will create your ROA. So based on the information that you provided, it will create your ROA. So the signing process, because it is quite a heavy process, it's a crypto process, it takes a few seconds to happen. So there is a signing process, and we have a timestamp on at what point in time Afrinic created that ROA. Then once it's created, it is actually published. It is published in a public repository. Each RIO have their own repository, and it is a public place where what we call relying parties. Relying parties are special software that will come and download those objects for validation. So that's the next step actually. So what I've shown you on top here is the RIO section. So from the user query to ROA publication, it is the RIO managing the time scheduling and the orchestration up there. But down below, as soon as we hit validation, it is the ISP. So an ISP, you would want to filter incoming BGP announcement, right? So to do that, I would install a what we call a relying party software. The relying party software would connect to the Afrinic publication point, download the objects, validate them, and then produce a list of what we call VRPs that will be fed onto to routers for them to make the decision whether, should I accept this announcement? Should I drop that announcement? So there is a timestamp at the validation point. Then the next timestamp that we took is, so let's suppose an incoming announcement was let in. At what point in time we see those changes on BGP? So since we do not control we do not control on, for example, on the internet, who is actually providing this information, we rely on publicly available information, that is the route collectors that provide those information. And we see our announcement there, and this is where we do the collection of the data. And finally, we also run traceroute, because if our network is reachable thanks to RPKI, we can run traceroute, let's say, to our router that is advertising our prefix. So this is, we also collect data for traceroute. So basically, the minimum RTT, the round trip time. So the experiment itself, let me go into that one. So to do such an experiment, you need prefixes, right? And you need an AS on the internet. So we had an AS on the internet, and we managed to get prefixes from all the 5 RIOs, because our aim was to do a global study, not necessarily focus on one region. So the RIOs have special policies for those who want to do research. So anyone can go and ask for experimental resources. They would give you that on a temporary basis. So we got /24s and /48s, and the prefixes were announced from our AS, and they were announced to our upstream providers. Our upstream providers were doing ROV, but we also announced it to other peers that were not doing ROV, so that we know we can actually see the difference. And the measurements were actually taken over a year, so we have quite a good amount of data. So one thing that we had to do to be able to see the differences. So when we create a ROA, so we had to create what we call ROA beacons. So what is a ROA beacon? So first of all, for the prefixes that we receive, we had 2 sets of prefixes. We call, one is a control prefix, and the other one is a test prefix. The control prefix would always have a validating ROA. So it means that on the internet, those prefixes will be reachable all the time, right? And then we have a test prefix. The test prefix, we will change the RPKI status of the prefix. We will make it a valid, the announcement will be valid, and sometimes the announcement will be invalid. So by changing the RPKI status of our routing announcement, we can see at what point it appears, at what point it disappears on the internet. And we were basically announcing a ROA every 12 hours. So here is our beacon. So we have a prefix which we announce. So we create what we call an invalidating ROA. So we put a fake AS for our prefix, which means that it is invalid. But then, if we create a validating ROA, so we create a prefix, we create a ROA with our prefix, but with a good AS, so the AS from which we are announcing our prefix, it will automatically become valid. So the valid ROA takes precedence over the invalid ROA. Okay, so this is how we were flipping the status of the announcement. So in that particular study, we didn't really, so I was mentioning that the validation action also takes a bit of time, but in our case, we didn't really look into the validation time itself, because that's a separate study that eventually we will also do. What we really wanted to do to see the impact on BGP. So our question was very simple. If a network is hijacked, in how much time would a person be able to see the changes if a ROA is created? If a ROA is created to protect those announcements. So as I mentioned, we collected data from the right risk collectors, and then we used 2 collectors for that, RC00 and RC01, and that was good enough for us to see meaningful information. So some results now. So let's look at creation time. So we, as mentioned, we looked at all the RIOs, and we look at what point, when we create a ROA, at what point we see them happening on the different places that we are actually taking time. So for Afrinic, when we create a ROA, it is immediately signed. It is published in about 3 minutes time. So in brackets it's IPv6, so we did both IPv4 and IPv6. The relying party would take it around maybe 15 minutes, finish the validation, and for BGP, basically, we would see the impact on BGP around 15-16 minutes. Epinic is a little bit more, because they do ROAs by batches. So when you create a ROA in the Epinic portal, they do not create it immediately. They batch it. They batch all the requests together, and every 20 minutes they would create all the ROAs all together. So which means that there is an offset of about 10 minutes for Epinic, and this is why for them it is a bit longer. So basically around 26 minutes for it to appear on BGP. We found RIPE is also quite fast, almost as fast as Afrinic. But we found two major issues with ARIN and LACNIC, so which we reported to them, and they eventually fixed. Their publication time was extremely high, more than an hour or almost an hour, which had a very high impact on BGP. So for ARIN and for LACNIC, if you had to create a ROA there, it would have taken that long, 95 minutes or 51 minutes. And why was this happening is that we saw that they were signing their ROAs in GMT, but only publishing the ROAs in local time. So, and of course, RPKI, if the RPKI has a not before time, so not before is the time at which the ROA is valid. So if the ROA is set to be valid in the future, it will not appear in RPKI because it is not a valid ROA. It will only be valid if the not before time is as now. So we looked at the creation of a ROA. So we also look at the deletion of a ROA. So in some cases you would want to delete a ROA to fix your BGP. So here so Afrinic is very fast, around 34 minutes, 38 minutes for it to have an impact on BGP. Epinic has this 10 minutes delay, which increases a little bit, but the others were around 45 to 48 minutes. So we saw that in general, the revoke delay is a little bit higher than the creation delay. So here, 15 to 26 minutes, there more than 35 minutes. So why is the revocation of a delay higher than the creation of the delay? And our hypothesis was that so when you set up when your router connects to a cache, RPKI cache, you can actually tell them to have multiple caches. So if you have multiple caches, what happens is that when you delete a ROA, if one of those caches still has a validating ROA, your information wouldn't be updated. So you need to wait up and until all those caches that is configured on your router synchronize before you see the change. That is why you have this delay on the withdrawal side of things. These are just graphs to show that in our case our provider were NTT. So we saw that ARIN. It is just showing that ARIN here was a bit slower than everyone, and here we could detect the ARIN bug was very apparent here on our graphs. We looked also at how much time the tier 1 providers were actually also updating their announcements based on what they were receiving from us. And so this is also data coming from RIPE-Priest, and we see, for example, this is I think it is Liberty Global. It was around 30 minutes that they took So what it is showing here, it is that 80%, in 80% of time, it was around 30 minutes that Liberty Global was taking to show the difference, to show the update. We also saw that at some point there was a higher delay, and this was due to a bug in the Routinator software, which is one of the most used RPKI relying party software. There was a bug that got fixed, and eventually the time was a little bit better. Oh yeah, and finally we also took data. We also took the timestamp from traceroute. So now the data plane information. So how did that work? So our routers were announcing prefixes. So we could actually run traceroute from RIPE Atlas probes. So RIPE Atlas probes, as you know, are small devices that you can connect in any network around the world, and you could use them to run internet measurements. I don't know if Fergus brought any. Yeah? Okay. So if anyone would want to host a RIPE Atlas probes, Fergus has some in his bag. So we use those probes to run traceroute, and so the traceroute, the targets were our routers, and what we saw is that so when the green lines, I don't know if you see that clearly. The green line is when there was a ROA, and the red lines is when there were no ROA. So when there is a ROA, there were a lot of traceroute that you could do because the routing announcement was valid and everything. But when the ROA was removed, so our routing announcement was invalidated. So you could see, you would see, of course, no traceroute going to those to our endpoints. But in this case, because providers, they usually have, like networks, they usually have different providers. So, and each of the providers, they have different policies for RPKI. Some of them would refresh their RPKI maybe every hour. The other one would refresh their RPKI every 30 minutes. So the disparity of the policies of the different providers could actually be seen here, because there was some sort of path hunting happening. So if the traffic couldn't go through one network, it would go through the other network of the provider. So we could actually see that in our graph. So to conclude, there are two sections of delays, mostly the RIR delay, which we saw for Afrinic is very good. It's almost zero. When you create a ROA, it gets published there almost immediately. But where the bottleneck is in the ISP delay. And this is what we need to start thinking about how to improve those delays. So we could look at, so we saw that the relying party is a big bottleneck, and so we could look at how perhaps to increase the frequency of validation. Increase the frequency of validation, and yeah, there are some relying parties. They're not the most used one, but there are some relying parties which are not multi-threaded, so it takes them much more time to do the validation. So the problems, so basically BGP propagates in minutes. So if you want to create a BGP, if you create a BGP announcement, usually within a minute everything converges. So you would see the impact of BGP within a minute. But RPKI, it's in the order of, as we have seen, hours. So this might impact the time you need to repair a bad ROA, or the time you need, for example, to authorize a DDoS mitigator. This is obviously a study that we published. When we share the slide, you will find a link that if you're interested in that, you can have a deeper read on that, and it contains much more information that I presented today. And that's it. Thank you very much. If you have questions.
Do we have any questions? Hi, not directly related to John Brown, Team Company. What do you see, do you have any info from your study where you can show or see what the uptick or uptake of RPKI is across the internet?
Last time I checked, around 40% of all prefixes that are routed are covered by Aurora, right? So this is just the Aurora part, but the percentage of ASs doing validation, I might not have it in my mind, but I need to check. Epinic provided statistics. They have their Google Ads platform where they go and check who is doing ROV. And I don't have that information offhand, but at least for the prefixes, it's 40%, around 40%.
Jared Lodge for this, wearing my Akamai hat. Akamai has recently started doing ROV at the IXs, and so you should see that as a result that we will, not be following invalids as a result there. That may not be publicly observable though, because not a lot of people sit behind our network in a way that's observable, but that is something that is an ongoing effort. It takes a long time to actually get that on 3,000 plus routers and have that actually work the way you expect it. But that's something that we're gradually rolling out here through the end of Q1 and early Q2.
Thanks. RPKI ROV at IXs is quite an interesting thing, and we rely on our route collectors, which are hosted at IXs to understand who is actually, whether or not they are dropping the announcement. But one thing we noticed is that a lot of sessions at IXPs are also direct sessions. So I don't know if Akamai do direct sessions with their peer. And in these cases, it is difficult for us to actually understand whether they are actually enforcing ROV on those direct sessions. But yeah.
I can specifically answer on Akamai is that yes, we are doing that on those direct BGP sessions that are over the IX, and then we're going to be rolling that out to all of our private peers and others throughout like I said, basically Q1's done, so here in the beginning of Q2.
Excellent.